Up next, we have Anuj Mittal, popularly called the problem solver. He is currently pulling strings to keep the complex big data world simple and cost effective at Flipkart scale. Joining him today is Sunil Kumar. With over 16 years of experience in building teams, directing and delivering large scale business applications, Sunil is currently managing everything big data at Flipkart. Anuj and Sunil are here to talk to us about the challenges, journey, and future of managing hundreds of petabytes of data at Flipkart's data platform. In this talk, they will also be discussing exabyte of scale in next few years. Where are we heading? Whether private, public, or hybrid cloud is the way to go, and how and what do we do to optimize on this? Ladies and gentlemen, a big virtual round of applause for Anuj and Sunil coming up on your screens.
Good afternoon, everyone. I'm Sunil. We'll jump right in. I'll be talking about the challenges, journey, and the future of managing hundreds of petabytes of data at Flipkart data platform. Looking at the e-commerce and the big data scope all in India, starting 2010, we had the data, we had sparse connectivity across the data that was being used. Now, moving fast forward to 2016, this was starting to connect a lot of data insights across the data sets and was being used for doing all the cross selling, upselling, and utilize all of those information. Fast forwarding to today, it's literally a web of data. Even the collection of the data is interconnected, the insights has to be interconnected, and how things are working. Now, if you have to look at multiple domains or the business units, clickstream, logistics, orders, just looking at the clickstream, it drives business decisions, reporting, ranking, recommendations, etc. If we have to interconnect each of these different platforms, it would be a literal mess of data transferring from one place to another. This is where a central data platform comes in, where FDP powers large-scale data operations for connected data insights. Now let's quickly look into the journey. We started around 2013 to 2015. We moved from what we used to call as Bigfoot to Flipkart data platform, where we converted to push-based, validated schemas, self-serve reporting, and real-time order scale. We moved to common data models, reducing our processing time by almost 30%. Then we had a requirement for billing per org and how we started to provide the business intelligence to be. Then cohort analysis and the rise of FStream, which is the real-time big billion day scale with less than 5 seconds of latency. All of this is laid over with discovery and machine learning platform, which powers the predictions at Flipkart. Now, after all of this, we started to see a rise in the frameworks that are out there, the technologies, the versions, the different cohesion of different interfaces outside, whether it's paid, unpaid, commercial, non, all of those. So we decided to separate out the compute and storage and also open that up for people. If somebody wants to use somebody else's data in a different form, different framework, they can do everything in our data platform. This became instrumental, and we started moving towards what we aim for is the evolutionary architecture and the right experience with a reliable system and the right data policies. In fact, we have clickstream analytics, which is almost like competing with most commercial softwares which are not able to scale with our data sizes, which look like this: 4,000 data feeds every day, 60 billion messages every day, hundreds of petabytes of storage right now. A quick bird eye view of our architecture. With the data lake, we also separated out the compute and storage, as we just talked about. We have slight intelligent layer or engine layer, as we call it, the catalog service, orchestration engine, and query engine powering an API, which can be used by the tech using an SDK, by business team using BI softwares, and then finally by data science teams to generate insights and predictions for Flipkart. What are the big problems that we have seen? These are real problems that we have seen at Flipkart. Just one unoptimized job brought down 20% of the cluster. Just one change by a Kafka consumer impacted all of the consumers. We are seeing rare bugs, very edge corner cases turning into expensive system for us. Technical challenges is what we'll focus on. We are having different forces from different places. On one side, we have constraints of cost and elasticity. On the other side, we see that experience still needs to be catered with the right capability, usability, with a multi-tenant framework to utilize all the software, which gives birth to a range of technical challenges. We require guardrailing on top of all of the change in technologies that is happening in the system at a large scale, and also educate the governance in the system via enforcement or education. This gives birth to a complicated architecture for the data platform. Now, how do we solve this? What are the base principles that we use? Solving these challenges with the right experience. The guiding principles that we use are follow the 90-10 rule, where 90% of the use cases are platformized and 10% of them are handled specially. Then we also manage the workload classifications across tiers, business units, prioritized queues, etc. The data lifecycle being the most important one, we enforce some via software and some via education via sandbox or tiering. We finally also apply the degradation and recovery levers to be able to be used at the right time when unforeseen spikes are seen. Now we'll run a deep dive into the reporting experience, how it looks like, what are the challenges we have been seeing. A typical reporting experience, reporting service has data stores, it has reporting service, and finally serving to a UI layer. But the challenges that we see are there are surge of queries, especially at the time of sales, up to 100 times within seconds. And also we see duplicate queries. Duplicate queries can be attributed to something like a cricket match. When the match is going on, you keep on opening websites and keep on clicking refresh, but the data is not going to change fast. The queries are remaining the same. You're asking for the same thing across the users. So how do we manage that? All of that topped with resource constraints poses problem. All of this also leads to unpredictable response time. So how do we solve it? We have added some smart layers between our reporting service, which are the smart caching, request deduplication in a queued manner, and smart throttling. How do we do that? Jumping to smart caching, all of the requests that are coming to the UI, it goes to the smart cache. Now, how is it different from the regular cache? Regular cache simply awaits the data after a certain TTL time. But the smartness here is that based on the high frequency of usage, automatically we trigger a background refresh first so that the data is fresh enough for the people. But on the basis of frequency, we also decide that let's reduce the TTL of this particular request because this is coming often, which means people are looking for fresher data. If not, then it will evict at a longer duration. So it might be showing stale, which is not really stale information. Metric query deduplication. How do we do this? We see that same kind of a metric across dashboards, reports, users, and channels are seen. For example, an executive might be looking for number of orders for a certain geography, but a logistic, the operations guy who is actually on the ground delivering will be looking for this metric to actually make sure we have sufficient staff. So this is just one example. We see a lot of queries for the metric. So instead of looking at the dashboard reports email separately, we look at the matrix. The query for all of these metrics are deduplicated by a deduplication engine and then sent to the actual data source. This reduces our load from thousands of requests per second to thousands of requests per minute. That's the scale we're talking about. Now, smart throttling. Although we have limits of having certain queries in the queue and putting those to the data source, but we still assign for these queries a priority based on what kind of dashboard or reports are being used. For a critical report or a critical dashboard, a priority P0 is assigned. Now, for each of these queues, the allocation is different. So P0 will not suffer, it will continue to serve the request. But if the P1 is empty and P1 is having higher request, it will burst into P1 and vice versa. There are throttle limits for these as well. With the base limit, it is able to cater to the right experience for P1 and also serve fastest on the P0 queues. So the throttling itself is queued as well as prioritized across each other. What are the takeaways on this? 90-10 rule allows us to serve the 10% of the critical requests faster, and the remaining 90% in the permissible limits. We have the right design guardrails, which allows us to use the commercial off-the-shelf tools to coexist with the open source as well. Why are we saying this? Primarily because in terms of BI or reporting, there are many tools catering to different needs of different people at different levels. They will continue to coexist. So how is our design catering and allowing people to use all of those needs to be there, but the design guardrails should also be there. As we talked about smart throttling, we have data refresh windowing, as we just talked about, which removes the needless variability within the time window. With that, I'll hand it over to Anuj to talk about scale, Flipkart data platform.
Thank you, Sunil. Good afternoon, everyone. Let's dive deep straight in on the scale. Okay. So, what does scale mean at Flipkart? As you can see, the rate of growth of data in our platform has been exponential. And this has led to massive cluster sizes across all our tech stacks. With the storage growth and the mandate to ingest everything data can be used in future, our storage clusters are running at their brim. Now, this may be good from a business point of view, but for a platform team, this becomes an overhead. Now, how do we solve for it? Storage can be solved in multiple ways, but like Sudhir mentioned in his previous talk, tiering is where we placed our biggest bet. And we have different tiers: hot, warm, cold. Capacity per unit rupee increases as we moved from left to right. Now, at our scale, we need a system to automate this movement, and the system has some additional responsibilities. These responsibilities or these actions are performed using certain instructions, which are policies, and we have a discrete slabs for each of the policies. These policies are owned by specific owners and they use it in a self serve way. Now, with all of this, quite often we ended up in a situation where cluster is running at the brim, and it was quite tedious to manually configure these policies. So we invented a way in which I could say a desired state, and then this desired state system actually moves uh, the state from the current one to the desired state in an automatic manner. And we built a tool for this, which does intelligent automatic tiering, and we call it Bifrost. Now, with storage increase, compute is not far behind. Now, compute may not be strictly following the exponential curve, but as you can see, that the peak resource utilization is 10x of the available hardware. And while it is easier to scale compute because it's a stateless component, it's the objective function here is to reduce the compute demand because the costs of increasing compute are significantly more than the storage costs. So how do we do that? Some of the things that we employed: building APIs that encourage responsible behavior. For example, ensuring or mandating users to enter the expiry of any FDP entity they create. For example, entities created in 2013-14 in the journey that Sunil showed were still existing. So how can we mandate it at the creation time itself? Similarly, advanced configurations, allowing users to specify like speculation, helped workloads not be subject to few rogue nodes in the cluster. Sticking to a constant optimizing theme, allowing people to have job diagnostics for their uh, ever changing jobs and having them available after every run. Dr. Elephant solves for it. Or having an optimized storage format like ORC, which allows predicate pushdown, where massive data filtering is happening in the storage rail itself before that data is read into the memory. And finally, doing all of this while promoting reuse. Data engineering teams building common data models on common data sets like orders, or if multiple people are querying an order table, or there are multiple pipelines running on an order table, all of them are sharing compute and avoiding any redundant processing. Next, let's move to a very interesting topic, outdated technologies. Now, why are we talking about it? As we all know, technology is ever evolving, and platforms that do not adopt technology miss out on innovation. And not only innovation, it's very costly for the business to run on outdated technology. So, for the purpose of today's presentation, we are going to talk about Hadoop 2 to Hadoop 3 upgrade, a very popular Apache project. Now, the specific tech stacks which we are going to cover in today's discussion are the following: Hive, Yarn, and HDFS. And the state we are talking is when the industry has moved to 3.x and we were at 2.x, what are some of the key capabilities we were missing? For example, in the Hive layer, long lived analytical processing, which is good for interactive querying, ACID compliance. In the Yarn layer, ability to schedule compute containers on GPU, ability to define custom resource type, not just standard CPU and memory, and able to do a lot more things dynamically. And most importantly, in our stateful layer, where your bulk of your data resides, introducing techniques such as erasure coding, which claim to reduce the storage footprint by 60%, which is direct impact to cost. And for people who are aware of HDFS, name node for long was a single point of failure. With federation stabilizing in 3.x, that becomes and removes the single point of failure, making HDFS as a truly horizontally scalable platform. Now, a quick intro where we use these tech stacks. Hive is used as a query engine and a data warehousing solution. Yarn is used to schedule containers and manage our compute resources. HDFS is used to host our data lake on the underlying storage hardware. Now, all of this at massive scale. What are the challenges at massive scale? There may be many, but the two key or non intuitive ones from our point of view are abstractions. Now, when I say abstractions, it in the context of an upgrade, it means any of these 4 lakh queries or workload may be using multiple user defined functions for Hive or multiple libraries to schedule their compute. Slowly over a period of time, we get so coupled with the implementation that even the minor version upgrades are expensive or they break, let alone the major version. So that's a big challenge to solve at such a wide scale. Other thing is you have all your users running 24/7 the queries, and you don't want any of their workloads to be failing or they having a degraded experience. So how do we go about it? What's the approach we follow? First things first, for such a large migration, you need to have some philosophies in place. What are those? Having a clear vision. Now, vision can be an overloaded term, but for us specifically, when we are talking about upgrade, what matters is the version that you are going to. How long do you see it sustaining? If it is only for a few months or days, there is no point in going to that version. And at the same time, can you club any other major tech debts or upgrades with the same thing, because it's going to have a lot of redundant effort in the both the activities. Second, setting clear expectations. You need to clearly know that your objective functions or metrics that is going to be impacted when you are doing such a big upgrade without making it ambiguous. For us, it was massive cost savings when it came to storage, and resiliency when it came to compute. And finally, you are doing all of this so that your users can have a good experience. They can work with the latest and greatest, and your business can effectively scale better. So communication and taking your stakeholders into confidence is very essential. Now let's go to the strategy, and let's talk about what is the architecture that is going to be in place during the course of such a migration. Now, by design, 2.x and 3.x is interoperable, meaning I can have workloads that could be communicating across both the versions of stack. But does that mean I can do in-place upgrades? Let's look at some of the risks with the in-place upgrade. One risk that any in-place upgrade poses is a chance of a data corruption. And for us, it could be a permanent data corruption, which is irreversible. And from our past experience, we have seen within minor versions of these components itself, there have been breaking changes or compatibility issues. For example, when we upgraded from yarn 2.7 to 2.9, lib Hadoop jars had a conflict which failed the localizations of the framework jars like MapReduce on the system. So in-place upgrades for us was a definite no. What next? So naturally, if in-place upgrade is not possible, I'll have a parallel stack in place. And my beginning state would be all my resources are running here. And this is just on plain paper with no resources employed. Now, does that mean I'll ask for 2x the hardware? Obviously not, because at our scale, both cost wise and the amount of operations that I'll have to do, given it is going to be an activity that takes weeks or maybe a month, that's certainly not possible. But if I can build a proposition where I say 20% of the hardware is what I need as a buffer, it becomes feasible from resourcing point of view. But how do I achieve it? Given specially, Sunil initially told, it's an interconnected web, which means it is very hard to break it in between and say some parts run here and some parts run here. So we'll have to chunk it. And we'll have to chunk it in a way that I'll able to release some capacity from 2.x in an incremental way and employ it in 3.x in an incremental way, and repeat this process till the migration completes. Now, how do we do chunking? We'll come to it later, but let's continue with the architecture first. So next, naturally, does it mean I'll have to have two data copies? Now, what are the problems with two data copies? I'll have to ensure data sync. They are in sync with each other. And even if they are in sync, in case they diverge, what is the source of truth that I trust upon? Now, before I go to how we can solve about it, let's see if we can narrow down our problem statement or reduce the scale of problem. The HDFS 2.x and 3.x is where your majority of data is lying. So that's very huge scale, and it is very tough to keep it in sync. But can I reduce the problem statement to saying I'll sync the Hive data, which is just the metadata sync, which is significantly lower in data volume. So let's see if we can sync the metadata. So just double clicking on Hive architecture, there's a Hive query server which parses the queries. There is a meta store, and the MySQL is where your metadata lies. And parallelly, you will have the same thing for 3.x. Now the problem is you need to sync these MySQLs, and with all the jugglery we tried, in sync replication, etc., we were able to manage data sync. But source of truth is still a problem. Why? Because both of these stacks will have their independent reads and writes, which means MySQL can diverge and the state of MySQL can diverge at any point in time. So this is not a valid option. So what do we do? Can I have such an architecture? If I have such an architecture, how do these problems change? I'm only dealing with one copy. There is no data sync required, and there is a single source of truth. Now, how was this made possible? With all the failures in the previous step around syncing, what we discovered was a key thing. With little effort, Hive 3 DB schema, physical schema, was backward compatible with Hive 2, where I'm just adding columns to few tables and only adding tables. All of this was non-trivial, as to make it happen, we had to cherry pick SQL commands from Hive 3 code base, do a bunch of bug fixes, have a soaking period for 2.x, and then only attach 3.x. Next. Now with this architecture in place, do any read-write problems occur? Remember, we have only synced Metastore. The HDFS data lake is still different. So that's definitely a problem we need to solve. And there is interdependent data, meaning any data lying in 2.x, I should be able to read from 3.x stack. And any data lying in 3.x, I should be able to do vice versa. Now, let's see how we can solve this. For our purpose of discussion, we'll consider table as our granularity level, because read and writes across tables are mutually independent. And we assign table in such a way that there are writes happening to only one table, which means for a table, we define its primary either 2.x, or 3.x, meaning its query, its compute, its location is on one stack. But reads, as put in the requirement, are allowed from both. And this primary is nothing but your actual data on HDFS. With this, our architecture is solved. And while we can have many key takeaways, one important or non-intuitive takeaway is to deep dive and look at the abstraction layer below you are working in. For example, in this, if we hadn't looked at fixing some of the open source issues, this migration would have been a non-starter. Now, any strategy is as good as its execution. With this stack in place, my workload is still running here. How do I switch it to this place? What is the order I follow? In a typical data platform, data is moving from left to right, where it is landing as raw data, it is being scrubbed, and finally it is ready for consumption. The data maturity increases as it moves from left to right. The data at this end of the spectrum will be highest quality, and the data at this end of the spectrum can have bugs, it can have validation issues, etc. Other important thing, characteristic of data to consider is from your business point of view. There'll be long tail of pipelines that will be there, but they are not as time critical. Whereas some of the reports or business executive reporting will be very critical. So now with all of these data characteristics, you define a fitness function. You formalize these things and get your sorted order of these 4 lakh queries as an output. What next? Now I cannot migrate these 4 lakh queries even if I have a sorted order in one chunk or one query at a time. So now coming to the chunk. What size do I move in? Now before we decide that, let's see how do I measure the progress of this migration or this execution. There may be a couple of ways that come to mind. One is the number of queries that have moved, or the number of resources that I have transferred from the old stack to the new stack. Now imagine a situation where after migrating, some of your queries fail. You will have to roll back the query. But can you roll back the progress? No, you don't want to roll back the progress. That will not be something intuitive for an end user. At the same time, resources also you don't want to move back, because it's a physical transform from here 2.x to 3.x. You don't want to move it back because it's very tedious. And resources are your real constraints. So resources is where you will pivot and define your progress. They share a same property, being irreversible. And with this, a basic principle that comes out, you go forward in a chunk and only uh, fall back for selective queries where you don't have to shift your resources back to the primary cluster. And in your fitness function equation, new parameter gets added. And this parameter defines, for example, if you define a capacity chunk of 5%, it'll take 20 iterations for you to migrate the data. Next, any execution is not complete without verification. And verification is costly, both in terms of time and resources. Now, there are various techniques, the whole spectrum of validations that you could do. Shallow will be cheaper and time effective, whereas deep will be costly. And you can follow various algorithms, techniques in this whole spectrum. Now, certain workloads that are redundant or mature, where these are pretty straightforward, you could do a count based match. Whereas certain other workloads, and going to the other end of the spectrum, your critical workloads where you need absolute consistency, you don't want even one row to be not correct, you trade off cost and try to do deeper validations. With this, verification also gets solved. And this is our final fitness function. Now, a key takeaway for such a migration is that it's very easy to think of migration manually doing in Excel sheets, but it's important to define a formal fitness function that can guide your change. And this is something that the entire team can use to unambiguously know what is the flow of execution. Now, we achieved this end state with this strategy and execution, but it had its own challenges. We had to coordinate across thousands of stakeholders internally, 150 systems were interacting with the platform. We had to fix a lot of open source bugs. These are some of the salient ones where some of them are not even solved right now in the open source. And all of this we had to adapt to FK environment where we had to apply some custom patches. With this success, what did we achieve? Like I said in the beginning, the cost was our major factor. And this is what we ended up achieving, apart from being on the latest and greatest tech stack. All of this without degrading any user experience. Some key byproducts. Now, 4 lakh queries definitely have some finite patterns. Today, if I change a single line of code or I introduce a new technology, I have a ready-made test suite to test it. The other key thing is moving from Cloudera distro to our own FK custom distro typically moved our architecture to be no vendor lock-in. Now, this doesn't mean that I'll not be using proprietary softwares in future. It only means my architecture is not hostage to proprietary software. Now, with all of this exercise and the journey that we went through, all our learnings, our architecture definitely became predictable for next few years. But the key learning that we will like to take away is have an evolutionary architecture, which basically means any future upgrades that I do with all the byproducts and learnings, I can have faster upgrade cycles. Now, what does our future behold for us? Looking back at this slide, which Sunil presented in terms of challenges, and we are dealing with on all fronts, but then there are some key focus areas for immediate future. And some of them include constraints around capacity, BCP and scaling out operations as the size is increasing, and doing this while continuously enhancing experience for our end users. Some of the new initiatives that we plan to take are around standardization. With more variety of data that is coming in, it is essential to have producer and consumer contracts, metrics that can explain itself. using best of both the worlds. I think someone asked Sudhir in the previous slide, we intend to use best of both the worlds. Finally, in such a huge cluster, reducing operations by system automatically detecting remedy and detecting issues and automatically applying some remedies. Finally, all of this culminating into intelligent insights where people can see patterns, our analysts can see patterns which otherwise they may not be looking at. Thanking you for patient hearing, leaving you with this quote. Thank you.